So it wasn't that long ago, it was just this morning in the seminar we were talking about this. I'm not going to spend a lot of time reviewing why this force happens, other than to say when you have a charge in motion, there's a magnetic field around the charge. When that charge in motion, which has its own magnetic field, enters a second magnetic field called an external magnetic field, then there's going to be a nudge on the particle. It's going to be forced. It's going to be pushed or twisted or pulled, however you want to look at it. And you could use the right-hand rule to determine the direction of the magnetic force. In addition, we now have a formula that allows you to calculate the magnitude of the magnetic force. Remember that the V in that formula is the perpendicular component of the velocity. I want to just draw your attention to something else that I know I've mentioned in the past, but I haven't been stressing it. You keep seeing this phrase, motor effect. The lesson from yesterday was called part 1 of the motor effect. The lesson today is part 2 of the motor effect. The lesson tomorrow will be part 3 of the motor effect. And a motor, at least an electrical motor, takes motion of charge and produces forces. I'm going to say on the output. So if you plug an electric motor in, or you have a little battery-operated car that uses batteries, the batteries cause a flow of electrons through a circuit. So there's your motion of charge. And the output is that the car is forced. It moves in a particular direction. So even though when we talk about this electron or proton or whatever it is being forced, even though when we talk about this, it's just a single charge, the principle is the same as if it were a whole bunch of charges moving in a wire. And this is why we call it the motor effect. So in the motor effect, you put basically electricity, movement of charge, in, and what you end up getting out of that is a magnetic force. So that's kind of where we left off this morning. We went over question 9, the second question 9, I think. But I think there might be other questions. Does anybody have any other questions you would like me to go over? Yeah. Okay. So we want to know the magnitude and direction of the magnetic force on an alpha particle traveling upward with a particular speed through a particular magnetic field. And my first reaction in reading this, I have to slow my brain down because my brain was looking ahead going, you don't know anything. You don't know the strength of the magnetic field. But when you look at the formula, magnetic force equals Q, I'll put in all the details here. Q, I don't know if that appears that way on your formula sheet. I think it should, but you know, the formula is kind of a scalar formula. We don't worry about directions in it. We do the directions with the right hand, okay? So when we look at this, what's important is the perpendicular component of the velocity. The number that goes in for V is the amount of the velocity that is at right angles to the magnetic field. And in this particular case, we have a magnetic field that is directed down. Now, I don't know if you're going to interpret down as towards the bottom of the page or down as towards the floor. Quite frankly, it doesn't matter. The magnetic field is down. And we have an alpha particle. So this is an alpha particle. It's positive, and it is moving up, which means it's moving in the opposite direction to the magnetic field. And if I were to ask you, looking at that vector of 2.11 times 10 to the 5 meters per second, what is the horizontal component of that velocity? And what is the vertical component of that velocity? you should hopefully recognize, everybody, that the horizontal component is 0. It's moving entirely up. It's not even moving just a little bit this way or that way. It's perfectly up. And then the y component would be the entire velocity, 2.11 times 10 to the 5 meters per second. And we've kind of talked about this in terms of momentum vectors and their x and y components this year. Now, when you start to look at the direction of this magnetic field is down. So in this question, this has to be a horizontal component, because horizontal is perpendicular to vertical, which is the magnetic field. And what that means is that the magnetic force will be 0 because the perpendicular component of the object's motion compared to the field is 0. Does that make sense? It's why I always tell you, in order for you to get a magnetic force, the moving charge has to be going across field lines. It has to be cutting through field lines. Even if, I didn't draw a very straight line here, but even if this was just angled a bit, it's going to be cutting across field lines as it progresses through the field. And you can even think of it this way. The more rapidly it cuts across field lines, the greater the force. So something moving in that direction is going to kind of clip across a field line every so often, but something moving with the same speed this way is going to hit field lines quicker. It's going to cross them more readily. Does that help? Okay. Any other questions? Yeah. Okay, let's look at number 10. There is a typing mistake in number 10, and it's not an insignificant one. It's an important mistake. It says equals something times 10 to the negative 14, and then I believe I had typed Tesla, and it's not Tesla. And the reason why I think that's a really bad mistake for me to make on your note package is I looked at it and I scanned for what I was after, and I saw I was after Tesla. So I thought, oh, well, I'm after the magnetic field. And then I looked at the question and I said, yeah, but we know the magnetic field. So I got confused. It should say newtons. This is one very similar to what we just talked about, where we have to look at the component of the velocity that's perpendicular to the magnetic field. Now, I mean, Farhan, you and I had a conversation yesterday about theta, and it turns out that in the examples we've done so far, to find the perpendicular component, you use sine of theta, okay? But it may not be sine of theta all the time, okay? And I'll show you why it won't be. I believe it's going to be sine of theta in this example. But when I take a look at the magnetic field, so I'm looking at a map now, just to let you know, the magnetic field is towards the south. Okay, so on a map, north is up here, east is this way. So the magnetic field on my flat map is towards the south. And the particle is traveling along the surface of the Earth at an angle of 70 degrees west of north. So what does 70 degrees west of north mean? North is this way. West of it is that way. So 70 degrees west of north looks like that. And that's the direction it's moving in. So when I now look at the horizontal and vertical components of that vector, or I could have drawn them this way, the horizontal and vertical, but I didn't draw them that way because I want to include that 70-degree angle. I want a triangle that has that 70-degree angle. And I look at those two green vectors that I've drawn, everybody. I ask myself, which of them is perpendicular to this field? Because in the formula, that's what we have to use. We have to use the perpendicular component of the velocity. And the answer in this particular case is it's the horizontal. So I'm going to find the horizontal component here using this triangle. This is V perpendicular. And when I do that, I can see that the thing I'm trying to find is opposite that 70 degrees, so I can use sine of theta. Might as well write sine of 70 degrees equals the opposite over the hypotenuse, which is how fast it's moving. And we got a little bit of legwork here to find out how fast it's moving. You're told it's moving 5% the speed of light. Maybe what we can do is just go to a different page momentarily. What is 5% the speed of light? That's 5 over 100 multiplied by the speed of light, which is 3 times 10 to the 8 meters per second, which you can look at on your formula sheet, but we have the next unit is called electromagnetic radiation, which deals with, among other things, light. So we will become intimately familiar with the speed of light in the next unit. So we multiply that out and you get 1.5 times 10 to the 6. I don't know. No, times 10 to the 7. Is it 1.5 times 10 to the 7? Okay. Thank you. And that means that this hypotenuse is 1.5 times 10 to the 7 meters per second. So now we're just about home free. We're going to put 1.5 times 10 to the 7 here. We can calculate V perpendicular to put it in here, along with the charge of the proton, and then multiply by the magnitude of the magnetic field as well. Is that okay? Okay. Now, we ended up using sine here. But what would the answer to this question be if, so I'm trying to figure something out while I'm working on this, if the question said that the magnetic field were, say, west? I mean, if the magnetic field were west, that would change things. Because when you look at the two components of this velocity, the one that's perpendicular to west is this, which happens to be adjacent to the 70-degree angle, which would mean that you'd have to use cosine. And I'm just saying that because I don't want everybody to get complacent, which means just assume it's always the same way and say, oh, well, it's always sine of theta, it's always sine of theta. It's not. I mean, we can go back to the original question here, forget about magnetic field to the west. Let's say it was that way, but I didn't tell you it was 70 degrees west of north. I told you it was 30 degrees north of west, which is the same. Thank you. That's what you were doing, 20 degrees. I always get that extra 10 degrees in there somehow. What if I said it was 20 degrees north of west instead of 70 degrees west of south, or west of north? So this would be 20 degrees in here. It doesn't change the answer to the question. It would be the same, except that you would be working with 20 degrees, and the component that's perpendicular to that south is the west, which would be adjacent to the 20, which would mean you use cosine. And maybe my more general point is draw a picture. Make sure you know whether you're going to use sine or cosine, and you have to take it on a case-by-case basis. It's not always going to be the same. Anyway, you're okay with that now? Any other questions from the assignment? All right, so seeing none, we're going to move on here. We're going to be looking at part 2 of this motor effect. Part 1 was moving charges in magnetic fields. Part 2 is moving charges in magnetic fields. Part 3 tomorrow will be a little bit different. We're going to continue to work with the formula magnetic force equals QVB, because that's how you find the magnetic force acting on a moving charge. Okay? So we're still using that formula, but our calculations will be used for a different reason than just finding the force. So the first example says We have ions, and the charge of the ion is given to you, and the mass of each ion is given to you. Some of you had asked, and I apologize for not getting that assignment marked and back to you yet. It's in my to-do list. And normally I get things back quickly. With everything going on, I've lost track of things. Somebody had asked, though, with that assignment, I can't remember who, it doesn't matter. It says a beam of electrons in the assignment. And then the person was questioning, well, can I just analyze one electron? Because it's a whole beam, right? And my answer to them was yes, the physics that describes the path of a single electron will describe the path of every electron, and that's what collectively forms a beam. I mean, if we're all going this way in a line and we all move the same way to the right because of a certain force, maybe it's the force of an ice cream stand attracting us, then our path will be bent that way, right? And even if we're walking shoulder to shoulder or one after the other, if everybody moves that way, the beam moves that way. So even though this is a beam, we can talk about a single ion in our analysis. They travel perpendicularly, and this is perhaps the most important aspect of this example, is that they're initially moving perpendicular to the magnetic field. And you're given the strength of the magnetic field and you're given the velocity. And by the way, that is enough for you to be able to calculate the force on each ion, but we're never going to do that in this question. You'll see why in a bit. Describe the motion of the ion in the field. This is a very difficult thing for me to explain. But let's just say, which way do I want to do it? Let's assume these ions are positive. And I'm going to assume the magnetic field in the room that they're traveling through is towards the floor. Okay? And I'm going to assume that all of a sudden they're injected into the magnetic field that way. I'm doing this for the ease of my right hand. So we have a magnetic field that's towards the floor, and we have positive particles that are moving that way. So if I said, what is the direction of the magnetic force on the particle when it first enters the field, you would point the fingers of your right hand towards the floor. You would point your thumb of your right hand towards the left side of the room. You would look at the palm of your hand and you would see it's facing the back of the room from your perspective, which would mean they would be forced towards the back of the room. But what's that going to do to them? Let's take you really have to wrap your brain around this. Let's take a top-down view of the room. Okay, so this is the room that they're in. This is a top-down view. And I said the magnetic field was towards the floor. So how do we write that? Towards the floor would be in. And we're just in a learning mode here. I don't know the value of you actually writing down what I'm drawing here. And the particle enters here. It's positive, and it's moving left. That's what I said, right? So if we pick this whole room up and tip it up like this, and if you're watching this on video, you don't see what I'm doing, but we're looking down from the top, from the ceiling to the floor. It's moving to the left. So it's moving this way. And as soon as it enters the magnetic field, I'm going to nudge this over just a little bit. As soon as it's in the magnetic field, this is the direction of the velocity. This is the direction it's moving. As soon as it's in there, it's forced this way. Right? That's what we said. Are we okay with that? It's a right-hand rule situation that we're looking at in real life, and then I've put it on paper. Now, this is the net force. And the reason it's the net force is quite simple. It doesn't mention any other forces. That's the only force acting on the particle. Okay? It's the net force. And that means that there is a non-zero net force. And that means the particle accelerates. This particle will accelerate. And what I'm really teaching you right now, if I can learn how to spell, what I'm really trying to teach you, I'll get it, acceleration. What I'm really trying to teach you is something from physics 20, believe it or not. This particle has to accelerate because there's a non-zero net force. But this net force is at right angles to the direction it's moving. So, can the particle speed up? And the answer is no. Since this green force has no part of it, no component of it to the left, this green force cannot increase the length of the red velocity vector. No part of that force is acting to the left, so the particle can't speed up. On the other hand, no part of this magnetic force that's towards the bottom of your screen, no part of that is to the right. So no part of that force can make this velocity vector shorter. So the particle can't slow down. And we seem to be at odds here. Many of you probably in your head, I'm telling you that the particle will accelerate, and now I'm telling you, but it won't speed up and it won't slow down. We need to remember that acceleration is a change in velocity, and velocity includes direction. So what happens is it changes direction. Now think about this for a second. If it changes direction, that means it's going to be off of its path and it's maybe going to be here now. Are you with me? Which way is it forced now? Well, now it's moving in this direction because its direction has changed. So when I point the fingers of my right hand in to the screen and my thumb in the direction that it's moving, the force is this way at right angles. And it's just going to keep doing this. So what type of motion are we talking about here? Where you have an object continually changing direction but moving at a constant speed. There's a special name to it from Physics 20. See Anna? No? You twitched. I saw your hand move. It's circular or centripetal motion. If I'm moving this way in the room, left to right, and there's a piece of rope that's attached to me, I'm wearing some kind of a harness, and there's a piece of rope, and it's connected to a pole, then that pole is going to pull me in that direction. If all of a sudden I appeared out of nowhere moving that way, it's going to pull me to my left. But all that's going to happen is it's going to continue to pull me in a circle. It's going to just go around. So what's happening here is this is the situation we have. We have the force, it's a magnetic force that's towards a central point, whereas the object is moving and it's moving perpendicular to that force. So in answer to this question, describe the motion of the particle. It follows a circular path. Give me a second, I just want to check on something. Okay, it follows a circular path. I don't quite know why this is important, but sometimes the diploma exam thinks it's important. Sometimes you're asked to compare the direction or the path, rather, of a charged particle moving through a perpendicular magnetic field to the path of a charged particle moving through an electric field between two plates. This is circular. The electric field between two plates produces a parabolic path. That charged particle in parallel plates will never turn back on itself. By the way, when I take a look at this, the way the particle enters the field, it's going to exit the field, right? It never completes a full circle, but if this is the field here, this part inside of the field will be circular. It doesn't mean it travels in a full circle. It just means the path has a circular shape. Okay, so now what we're going to do is find the radius of the circular orbit. And the most important thing, I guess, for you to remember is that the net force for centripetal motion is ma. Okay. How many of you were taught last year this formula? In fact, how many of you remember this formula? Can you find it on your formula sheet? Good luck, because it's not there. Okay. And when I teach Physics 20, I show the formula, but I say, look, you're going to see this formula in your textbook, but it's a formula that's not on your formula sheet, and there's a reason for that. There are electric forces, there are gravitational forces, there are magnetic forces, there are frictional forces, but there's no such thing as a centripetal force as a type of force. The fact of the matter is, if an object is moving in a circle, there could be 100 different forces acting on it, and the net result is it moves in a circle. So really, what I would like you to appreciate here, and then we'll get to the question, this should all come together, is that the centripetal force is the net force. It isn't a special type of force that we have a formula for. The centripetal force is the net force. And right now, as a student, I can imagine you're sitting there going, I don't understand your point. Okay, you will in a minute, but I really want to drive home the fact that all a centripetal force is the sum of all of the forces acting on the object causing it to move in a circle. It's the net force acting on the object. It's not a different force. Okay, it's not like a gravitational force. It could be, but it's not necessarily. So when we solve these problems with centripetal motion, what we want to start off with is this statement, F net equals ma. And then what we want to say is that this net force is the magnetic force, which is QVB. Why is the net force the magnetic force? Well, the reason for that is, and listen to the language, the net force is the magnetic force. There's one force acting on this particle in the beam. It's a magnetic force. So the net force is that magnetic force. I'm not saying there are two forces that happen to be equal. There's one force, and you can describe the force that is acting on these particles as magnetic, or you can describe it as being net. It's the same force. Am I allowed to do this? I am. It's the same force. It's not like they're opposite to each other. There's one and the same. You don't need to do that. We can get by with just saying that the net force is the magnetic force. So how does this come together? The magnetic force can be calculated using QVB. How do we calculate net force? ma. But the acceleration here is a very unique acceleration. It's called centripetal acceleration. So it's at this point that we rewrite this as QVB equals M sub C, MA sub C. Look, I could have just written the C above, but I want you to note that the thinking doesn't go directly from the first line to the third line. The thinking is as we get deeper into the course, you will find more and more situations where we have to derive a formula. And there's lots of different formulas we're going to derive. What we asked for, the radius, that means the radius is mv over qb. All of those numbers are in the question. I'm just going to write this here, R equals mv over qb. So we have to take the mass, which is 2.29 times 10 to the negative 26, times the speed, which is 8 times 10 to the 4, and divide by the product of the charge and the magnetic field. So I'm going to divide by the charge of 4.8 times 10 to the negative 19. I'm also going to divide by the magnetic field of 0.120 Tesla. So I get this number, 3.18 times 10 to the negative 2 meters. Anybody else? So about 3.2 centimeters is the answer to the question. For B. Any questions with B? All right. So the next question is also dealing with a force analysis. We've got an electron or a beam of electrons, doesn't really matter, moving at 258,000 meters per second. It enters a region containing two fields, an electric field and a magnetic field. We want to find the acceleration at that point of entry of the electron if the magnetic field is into the plane of the paper. So let's take a look at the diagram. So we have a magnetic field that's in. This is going to get confusing for some of you. We have a magnetic field that's in. I don't care if you draw this or not. I'm going to. This is the magnetic field. We also have an electric field because there's a positive plate at the top and there's a negative plate at the bottom. I would like everybody to determine the direction of the electric field between the plates. I'm really happy to see that nobody's looking at their hand because it's electric. It's got nothing to do with magnetism. It's from the positive to the negative plate because you imagine putting in a positive test charge. So we have that magnetic field and we also have an electric field. Now, I don't know how you want to communicate that to yourself. I'm using colors. You should note that these two arrows, the B equals and there's an arrow, the E equals and there's an arrow, they're just pointing to the region between the plates. They're just saying that in here, those are the two field strengths. So let's take a look now at the question, what is the instantaneous acceleration? So what we need to know is the net force so that we can determine the acceleration. In example 1 today, the net force was the magnetic force because there was no other force. But in this question, the net force is going to be the sum of the magnetic and electric forces acting on the particle because there's two different fields. Because there's an electric field, is it an electron? Okay, thank you. Because there's an electric field, the electron will experience an electric force. Because there's a magnetic field, the electron will experience a magnetic force. Now that means, and we can calculate them. In fact, let's do that. Let's calculate the magnitude of the magnetic force using QVB, and let's calculate the magnitude of the electric force using QEB. E. So these are the two formulas. To calculate a magnetic force, you go QVB. To calculate sorry, lost my train of thought. To calculate an electric force, you go QE. To calculate a magnetic force, you go QVB. Well, let's just calculate the magnitudes of them. So can you do that for me, please? Can we agree on those two forces, the numbers? So how do we add them? Well, it depends on their directions because they're vectors. I mean, what if the directions are like this? What if the directions of those two forces are perpendicular to each other? They're not. I'll tell you that right now. But if they were, we have a certain way to add them. If the two forces that I've just written down are in the same direction, then we can just add the numbers together. But if they're in opposite directions, we have to subtract the magnitudes to get the total. So, what is the direction of the magnetic force? What is the direction of the electric force? I'm going to pause there because I'm just seeing a couple of furrowed brows. Are we okay with these numbers? Are you getting the same numbers? Okay. Evan, do you have a question? So you're not getting those numbers. Is anybody else not getting those numbers? Okay, well maybe we're the ones doing something wrong and you guys are not doing anything wrong. Let's check something, please. Do the numbers that I have up here on this picture match what you have? They do. Naya's found the problem. Yep. So there is a discrepancy in the question. How many of you got what I got? You and I used 2.58 times 10 to the 4. Everybody else used the 2.64 times 10 to the 5, or 2.58 times 10 to the 5. So since most people use the 2.58 times 10 to the 4, you and I, Makai, are going to have to change our answers, okay? In other words, I'm going to change this to 2.64, and I'm going to make a note over on the sideboard here to change my notes. Good eye, Naya. So I'm going to recalculate the magnetic force. It won't, the electric force, you would have got the same number. Okay, good. So I'm going to recalculate, and Makai and anybody else can recalculate as well, the magnetic force using 2.64. Is that matching? No? 2.64 times 10 to the 5 Is the magnetic field 1.8 times 10 to the negative 3? What did I just do here? 1 point. Oh, so I just typed in, there we go. Is that right? Okay. Okay. So 7.81 times 10 to the negative 17. All right, you guys got me back on track now. 7.8144. And we'll just take a breather here because of my ineptitude. Can we confirm the magnetic force is this number that's written down and the electric force is this number that's written down? Okay. And it's good that you put on that puzzled look because that tells me I have done something wrong potentially. So now back to the point here. In order for us to add those two forces, in order to add the two forces to get the net force, right? This is what we're saying the net force is the sum of them. You have to know the directions of the forces. And where I was at when I realized I did something wrong was, let's find the directions of those two forces. So I want you to look at the diagram, use whatever skills you have rattling around in your head, and determine which way the magnetic force is and which way the electric force is. Electron? So the electric force is towards the top of the page, and there's no mystical way I'm figuring that out. I'm just saying the top plate is positive, and electron's negative. The electron will be attracted electrically to the positive plate and repelled from the negative plate. So the electric force is going to be to the top of the page. The electric force is, I'll say, up. How do we determine the direction of the magnetic force? Now you have to use the right-hand rule. In the first part of this question, the magnetic field is in. So I'm going to just use the smart board. The magnetic field is in. The particles are traveling left to right, and they are negative, so they're forced out of the back of my hand, rather, which is towards the bottom of the page, so to the bottom. If you think you're looking down on a map, that works too. The magnetic field is into the floor, and the particles are traveling to the east, so they're deflected out of the back of your hand, which is south. And south on a map is towards the bottom of the page. So I can say down. That means since they are in opposite directions, to find the net force, to set it equal to MA, we're going to take and subtract the two. We'll take 7.8144 times 10 to the negative 17, subtract 7.712 times 10 to the negative 17. This is equal to MA, which is 9.11 times 10 to the negative 31 times the acceleration. So you can find the acceleration. One 1.1 times 10 to the 12. You getting the same number? No? Yeah? Okay, good. I think I carried all my decimals. You might not have, so you might get a slightly different answer, but 1.1 times 10 to the 12 meters per second squared. And we should put a direction on that. What direction will the acceleration be at that point in time? It will be in the direction of the magnetic force, because the magnetic force was a larger force in the opposite direction compared to the electric. You might wonder why the question says, what is the instantaneous acceleration? The reason is, as soon as that particle starts changing direction because of these forces, then the directions of the two forces will no longer be opposite. So the acceleration is going to change. We would never analyze what happens after that. It's too complicated. What if the magnetic field were out? Well, the magnetic force was, I'm going to go by memory here, 7.8144 times 10 to the negative 17 newtons. When the magnetic field was in, the magnetic force was down, correct? If the magnetic field is out, we can do it again. If the magnetic field is out, so if you're watching this on video, you can't see this, I'll try to describe it. My fingers are pointing out of the screen. My thumb is now, of my right hand, going to be pointing to the right side of the screen. And when I do that and I look at my hand, the back of my hand, which is of interest because the particles are negative, the back of my hand is facing towards the top of the screen. So that means the magnetic force this time is up. The electric force, on the other hand, and again, I'm going by memory, but I'm pretty sure I have this one as well, 7.712 times 10 to the negative 17 newtons. This electric force was up as well, or was up, because the positive plate is up top, and these are negative. So now to find the acceleration, you're going to take the net force and divide by the mass. But the net force will be the sum of these two numbers because they're in the same direction. Right? And boy, when these questions are on an exam, you got to work for your supper here. You got to really work to get that mark. It's a lot of work involved in answering this question. Either one of these could have been a multiple choice or numerical response. So 7.8144 times 10 to the negative 17 plus 7.712 times 10 to the negative 17 gives me this net force divided by the mass. That's not right. Divided by the mass of an electron, 1.1 times 10 to the 14. Boy, talk about a fluke. I don't want you to read anything into these numbers. It wasn't 1.1. Okay, I was going to say, that's really a fluke that this was 1.1 times 10 to the 12, and the other one's 1.1 times 10 to the 14. But apparently I didn't read my calculator right. You're saying it's 1.7? Okay. Well, it is a 7. Today was about force analysis. By the way, I could ask you, and I didn't, but I could. Were we done? Or was there one more? There is one more. I'm guessing it's saying how fast does it have to go so it's not deflected. See, I could ask you that. That's where my mind went automatically. And in that case, if it's undeflected, if it goes through the beam straight, that would mean the two forces, when it's in the beam, the electric force up and the magnetic force down, have to be exactly equal but opposite. And that would mean QVB has to equal QE. Do you agree that this is the magnetic force on the left, QVB? Okay. And this is the electric force. So those two things are equal to each other. Is this a true statement? Not this time. In example 1 today, when we wrote F net equals Fm, we could put vector symbols because it was the same force, just with a different label on it. These are different forces in opposite directions. That's wrong. You would have to write this. This is interesting. Charges cancel, and all you're left with is E over B. So all you have to do to find the speed is take the electric field strength and divide by the magnetic field strength. See how good my memory is. 482 for the electric. 0.00185 for the magnetic. Okay. So you take 482 newtons per coulomb divided by 1.85 times 10 to the negative 3 Tesla, which gives 2.6 multiplied by 10 to the 5 meters per second. Any questions with that final example? This is all about force analysis, these two questions. You can see what the assignment is. I'm going to guess that those page numbers are incorrect. No? Yeah, way off. 61? I don't know if it goes on to 62. It doesn't matter. I want you to get lots of practice with these problems. If you need practice with magnetic fields, field direction, hand rules, solenoids, there's a list from your textbook, but I'm going to warn you about something. Your textbook author uses left-hand rules. So my advice is don't go to your textbook to read how to use a hand rule because he uses left-hand rules. And I want you using right-hand rules. So I'll leave that up there for you, and you can get to work. You got a lot of time here today. Does this class end at approximately 20, 25 minutes from now? You got a lot of time to work on these. Get lots of practice. We'll go over them tomorrow. Again, your exam is looking more and more like it's next Thursday, a week from tomorrow.